Hey everybody, welcome back to the channel. Today we're going to talk about limb leads. Limb leads are 6 of the 12 leads that are on our ECG, leads 1, 2, 3, AVR, AVL, and AVF. And my goal with this video is to talk to you about how these leads are created and why they measure what they do. And so this will help you kind of understand all the diagrams. And so first thing let's talk about is what is a lead? Well, a lead is just a recording system, right? And so you have essentially an electrode here and an electrode here, and those electrodes are connected to a box. That's the ECG machine, we'll call it, right? We have our ECG machine, and our ECG machine can record electrical activity that passes along the plane that is created by these leads, right? Or these electrodes. And so we can have anything that passes along this plane will record signal. And so the ECG machine, what it does is it will actually kind of in its brain, it'll label one of them as a negative side and one of them as a positive side. And all that does is for orientation purposes. And so imagine this is how the ECG machine picks up signal. So say you have a signal, a bunch of positive forces that are moving along this plane from the negative side towards the positive side. The ECG machine picks that up as a positive deflection, okay? Now a couple things. The positive deflection itself, the height of the positive deflection depends on, the height of any deflection depends on two things. It depends on one, we will say the amount of force, right? We're trying to speak in normal terms, the amount, that's bad handwriting, the amount of forces, right? So that what I mean by that is for the heart, if there are a lot of thick muscle, right, the left ventricle, right, the more muscle that's conducting that signal, the more force you're going to have, right? And that's going to make it taller. Less force is going to be negative, right? And then two, the alignment. And so what I mean by the alignment is if it's going directly with it, right? The more aligned it is with the lead direction, the more likely it's going to produce a very high value, high in amplitude, right? And so from the other example is say we have a bunch of positive forces that are traveling along the axis of this lead from the positive to the negative side. Well, we're going to create a negative deflection. That's just how the ECG machine records these signals. And then lastly, say you have a bunch of positive forces that are traveling perpendicular to these leads. If they're traveling perpendicular to the leads, it's actually going to create something that is called isoelectric, where it's equally positive and equally negative, right? So we call this isoelectric, right? It could be even small deflections like that, but they're equally positive and equally negative. And so that is how a lead is created, right? And so we have a bunch of electrodes, right? These are the electrodes, right? The stickers that we put on people, and the ECG machine is able to create a series of negative and positive poles in order to record this, right? And so let's take a look at how the limb leads do that on the body. So as the name suggests, the limb leads are placed on the limbs of the human body, right? So the electrodes are placed on the arms. These are my electrodes. And on the legs, right? And so we have here, we have our right arm, we have our left arm, we have our right leg, and we have our left leg, okay? And so by using these 4 stickers, the ECG machine is able to create a series of leads in various directions to help us capture signal in those directions. And we want different directions because we want to get a 3-dimensional picture of what's going on with cardiac conduction. So the first thing I want you to realize is that this right leg lead, this is a grounding. It's a grounding lead, which means that it's just there to help balance out all the noise, right? It's there to cancel out all of the background noise, right? So this right leg doesn't really contribute to a lead, but the rest of them do. And so let's talk about those leads. And so our ECG machine is hooked up to all of these leads, and the first lead that it creates is a lead where it is between the right arm and the left arm. So it creates a lead that comes across from right arm to the left arm, okay? And in this case, the right arm lead is the negative electrode, and the left arm lead is the positive electrode. A lot of times you'll see kind of this depiction used where we put an arrowhead at the end where the positive is, right? And so this lead is called lead 1. And lead 1 is on the horizontal plane, and it measures signals that move from right to left and left to right, right? So if we have positive signals heading towards the left, in lead 1, we will see an upright deflection. On the other hand, if you have positive signals heading the opposite towards the right, we'll have a negative deflection in lead 1. So that's how we create lead 1. Lead 2 is created by the ECG machine when it connects the right arm electrode to the left leg electrode. And so lead 2, if you look at my arrowhead, my positive electrode that is measuring is now on the left leg. My negative electrode is here in the right arm. And so any forces that are traveling along this axis towards that left leg positive electrode is going to be our positive deflection, and oppositely, any forces that are traveling away along the axis are going to be negative. And then the last lead that is created from these 3, as you could imagine, is going to be between my left arm and left leg. You can see my arrowhead is telling me that I'm going to have a positive electrode at the left leg and a negative electrode at the left arm. Let me label this one lead 2 for you. This is going to be lead 3. And so, as you could imagine, any positive wave of forces traveling along this axis is going to create a upright deflection on the ECG, and the other way against the direction of the lead is going to create a negative deflection. So that's how we create our limb leads. And so what we can actually do with these first 3 of our limb leads, we're going to talk about the rest of the 3 here in a second, is we can actually create a triangle. So this is this is one of the triangles. It's called Einthoven's triangle. And so I want you to look at this triangle and see how we can essentially use the points to create a diagram. This is lead 1. This is lead 2. And this is lead 3. And notice that this triangle is an equilateral triangle. So these angles all measure 60 degrees, right? So that math is going to come in handy when we make this into a diagram that we can actually use to measure and quantify the waves on an electrocardiogram. So that's how we measure the forces on the limb leads. Notice that the limb leads are created on a coronal plane. So this is a coronal plane, which means that we are measuring forces along kind of superior, inferior, and lateral. Okay. And so let's talk about the other three leads AVR, AVL, and AVF. And so what's interesting is you're like, well, we only have so many stickers, so many electrodes. Well, how do we create these leads? Well, the computer, the ECG machine that's connected to all of these electrodes is incredibly smart. And what it can actually do is it can measure and create its own negative leads based on averages. So let's talk about AVR. And so AVR isn't what the machine will do is it will create a positive electrode out of the right arm, right? AVR for right. So it'll create a positive electrode out of the right arm. And then what it'll do is it'll measure the average between the left arm and left leg. And it'll create an average of the signals between the two of those, and it'll find a point right in the middle. And that is going to be the negative electrode in that lead. And so if I draw a line, notice that that line heads right to the right arm, and it is perpendicular to that lead. And so that's AVR. You can best remember that with the R for going towards the right arm. So it's perpendicular, notice, to the two leads or two electrodes that create lead 3. And so if I put it in the triangle, what does AVR look like? It's going to be perpendicular to lead 3, heading towards my right arm. So there we have AVR. AVL, you can imagine, is something similar in that we will have our positive electrode. AVL is the left arm electrode. It will average out here along the electrodes between the right arm and the left leg, finds the midpoint. That becomes the negative portion of our lead, and then a perpendicular line can be drawn towards the left arm. And so that is perpendicular to lead 2 as it heads in that direction. And that is AVL. And then the last one is AVF. It creates a positive electrode at the foot, AVF for foot, and then it measures the average here between the two arms, finds the midpoint, that becomes our negative electrode for that lead, and then uses 90-degree perpendicular angle to create AVF for foot. So if I drew it on this chart, straight down, and that is AVF. That's also perpendicular, right? Notice these are all perpendicular to one of the other leads because it's coming off the midpoint of them. And that's just because the computer can calculate those leads. It's technology that is beyond me. And so now we got this entire confusing contraption, but they all have angles because we know that the angles of the triangle are 60 degrees, and we know that off of leads 1, 2, and 3 are perpendicular leads that are leads AVL, AVR, and AVF. And so that triangle could be very confusing, and so it can be transferred into this nice circle that we have. And let's do that. So we notice that lead 1 is on this horizontal plane. So lead 1 is represented here, lead 1, right? All the leads are going to pass through the midpoint. We have lead 2 that is heading down and to the left at 60 degrees. So 60 degrees is along this line, and that is lead 2. Lead 3 is headed along in that direction, and if you do the math, it's heading along that direction at 90 degrees away from lead 1, and so we see that lead 3 could be represented by this arrow, lead 3, right? And so that angle that is created for lead 3 there, that's 90 degrees. Excuse me, that's 120 degrees, right? 90 degrees is going to be perpendicular. It's a little bit more. It's 120 degrees. I stand corrected, sorry. And then now, because we know that the other leads are coming off perpendicular to those, we can do that. So AVF is perpendicular to lead 1, and lead 1's horizontal. So this one's going to be straight up and down at exactly 90 degrees, AVF. We know that AVL is perpendicular to lead 2. So AVL, perpendicular to lead 2, going towards that left arm. So it's AVL. And the last one is AVR, which is perpendicular to lead 3. And that heads just like so. AVR. And so that is how we get this diagram. Now the interesting thing about this diagram, it's on the coronal plane, right? So if you slice somebody on the coronal plane in half, if you don't understand what that is, I would look up the coronal plane. And so this measuring forces along the coronal plane in all different directions, and this is really helpful. And so what I like to do is take that diagram for our leads, and I like to overlay the heart on that diagram in this fashion. And so this to me is really helpful to understand cardiac conduction. So let's talk about just some general concepts, and then you can just start to understand this as you look at ECGs. So the first thing that happens, the SA node is going to fire off, send a wave of depolarization through the atria. Notice that the sinus node is located high in the right atria, so it's going to head down and to the left as it depolarizes through the atria. So that means if it's heading towards the left, this is what's generating what? A P wave, right? Atrial contraction is a P wave. And so that P wave is heading towards the left. So in lead 1, right? Lead 1 right here, my P wave is going to be upright. Because we said if it's going toward, it's going to be upright. We said it's also going down because it's going from the top to the bottom. So my P wave in AVF, which is representing forces coming that direction, is going to be, in AVF, it's going to be a positive P wave. Lead 2, for the same reason, this force is going down to the left, so lead 2 is also going to be positive P wave. Now, if you notice AVR, these forces are going away from AVR, right? The positive electrode of AVR. So AVR is actually going to have a negative P wave. So there's just kind of some concepts there. Now, then the next part of depolarization occurs when the AV node takes that signal and sends that signal down to the ventricles. Okay? And when the ventricles depolarize, they're depolarizing in this direction generally. And we'll notice, what direction is this? This direction is also down and to the left. And so ventricular depolarization, we know, what does this create? This creates our QRS complex. And so ventricular depolarization creates our QRS complex. It's going down to the left, so it means it's going to the left, it's going towards lead 1. So lead 1, we're going to have a predominantly upright QRS. AVF, the QRS is going downward. We're going to have a predominantly upright AVF. Obviously, lead 2, which is measuring forces that are down to the left, will also be upright. But on the other hand, AVR, the positive electrode of AVR, is high and to the right, and these signals are going away from that positive electrode of AVR, along the axis of AVR. Remember, it's along the axis. It has to be going along that axis. And so AVR will actually have a predominantly negative QRS. And so then we'll also have our T waves, right? And T waves, I'm not going to really dive into it on this lecture, but T wave generally follows the QRS. And so that is the behavior of our limb leads. That's how we create our limb leads. That's what the limb leads are measuring. So a couple things that I want to leave you with these limb leads is that, one, understand their orientation on a coronal plane, right? A coronal plane. And once you understand that, understanding how they're created, how they record, what does the ECG machine use to record these deflections? And so when you see forces that are represented by certain anatomical aspects of the heart, you can understand what direction they're headed in when you put them all together, right? So you use data from every single lead. You use every single lead, 1, 2, 3, AVR, AVL, AVF. Which ones are positive? Which ones are negative? Which ones are isoelectric, right? If I had an AVL, if I had a P wave in AVL, which represents atrial depolarization, that was like isoelectric P wave. Well, that tells me that the P wave is going perpendicular to AVL. It tells me that my P wave would be going perpendicular to AVL, which is very positive. That's a very positive in the sense that it's very possible, right? You can use all those clues to determine the direction of forces and then the amplitude of forces. So this is just an introduction video. If you have any questions about the limb leads, let me know. The next video in this series is going to be on the precordial leads. So, yeah, hope this helps, and take care. Have a good rest of your day. See you on the next ECG video.